expected to finish these notes. I will be checking on them for our next check. And the key to this, we're going to look at circles and the measurement of related angle. And the key to this, to kind of, as you're going through the problems and we do some guided practice together, is ask yourself where the vertex is. Where is the vertex of the angle? So first major or new angle we're going to look at is what we call an inscribed angle. And I don't know if you noticed this. Angle ACB, this green angle that I have here, C is the vertex, and now this vertex, let me fix this real quick, sorry. This vertex is on the circle. Compare, when we're doing central angles, the vertex was in the center. Whenever it's on the circle, it's going to have a different relationship than what we did before. So, vertex C is on the circle. So, the inscribed angle is the angle ACB. The minute I look at the arc between that angle, okay, so it's the curve that's between the sides. Your sides are your lines, your chords. So, look at your endpoint. So, just go from A, this curve, to B. That curve is what we call the intercepted arc. And this would be arc AB. And we put the curve over the two letters. Okay, so the rule is, whenever I have an inscribed angle, a vertex on the circle, the measure of that angle, so for example, they gave us angle 1. That angle right there, that angle 1 is going to be half the intercepted arc. And let's do it this way instead of, let's write out the rule and then I'll put the, so the inscribed angle oops, is half its intercepted arc. Ran out a little bit of room. So basically this angle 1 is half the measure of AB. Okay. Now you can have one where you have a chord. Okay, this is our chord. I'm going to do the chord in blue. And you have a tangent. I'll do that side in red. It's still, the vertex is on the circle. Okay? So the measure between them, the measure of the angle, that angle is going to be half the measure of the intercepted arc. So I go from one endpoint all the way to inside. So right there, you could still have an inscribed angle with a chord and a tangent. Then what we're going to look at is using that relationship in different scenarios. So one of them is when you have an inscribed angle that intercepts the same arc. So you might want to do this with me, get some colors to help you see it. So if I look at angle 4, let's start with angle 4. I'm just going to highlight that. And I'm going to highlight it with purple. So here's my angle 4. Then I want to highlight its intercepted arc. I'm going to do that in yellow. The intercepted arc, look at it and see what curve is between the sides. Or where's the endpoint? D, yes, to E is the intercepted arc. Alright, now I'm going to get a new color. I'm going to go blue. And highlight angle 3. Well, angle 3 is D to G to E. And look what intercepted arc it has. It has the same yellow curve. So this is a correlate of the inscribed angle theorem. Basically says if you have an angle that intercepts the same arc, then those angles are going to be, you guessed it, congruent. Okay? They would be congruent. So if I look at this, I could say angle 3 is going to be congruent to angle 4. See if you can figure out angle 2 and angle 1. Do they intercept the same arc? So I'm just going to go a different color. Here's my angle 2. Where is this intercepted arc? That would be G to F. Does that have the same arc for angle? So this goes with angle 2. Does that have the same arc for angle 1? Sorry. Yes. So I can also say that angle 1 is congruent to angle 2. Now another corollary, or pretty much the same relationship with inscribed angles, is that an inscribed angle in a circle intercepts a semicircle, then it is going to be, think about this, so my inscribed angle, angle 1 here, there are the sides of that angle. The arc for that angle is what degrees? It's half a circle, right? So it's 180. Well, what's half of 180? Exactly 90. So that means that every time our intercepted arc inscribes with an angle that is half of that. So we have 180, half of 80 is 90. So this will always form, if you see in here, a right triangle. What is the measure of angle 1? 90 degrees. Alright, this next corollary is dealing with, we have a quadrilateral inscribed in a circle. Inscribed, like think inside a circle. So whenever you have a quadrilateral inside of a circle, the angles that are opposite each other are going to be supplementary. Okay, so I'm going to abbreviate sup, which basically means they equal 180. All right, we're going to pause right there. So because right here they're showing you that angle A and angle C add up to 180. If I know angle S is 100, then if I go across from it, that means Q would have to be 80 because it adds up to 180. And then if I go across from T, that means that would have to be 85 because it adds up to 180. Alright, and so the last two is dealing with when the vertex is not on the circle. We're looking at when the vertex is either in the circle or outside the circle. And in order to understand this, we need to highlight some key information. Now, if I have an interior angle, that means that the angle is inside the circle. It is going to be equal to the sum of the two intercepted arcs. That's very important too. So one of the arcs is here, arc Y, and the other arc is X. And then we're going to add those up. Okay, since we have the intercepted arcs measured or highlighted, whenever it's inside, you got to remember it's the sum, so I'm trying to finish this video, sorry guys. Basically, whatever the angle is, the measure of the angle, we're going to add the two arcs. So they kind of already wrote it up here. Angle A is half the sum of the two arcs. That's X plus Y. So if I know A and it's vertical to the angle over here, let's say we make that a B, then angle B would be half the sum of X plus Y as well. So here, if I want to find the measure of the interior angle, let's say I'm looking at interior angle, and I'm just going to put a number there, number 1. I need the intercepted arc. The intercepted arc for this angle would be here from, it looks like L to J, or I to J. Copies are kind of bad. And since it's vertical, we have a vertical angle, we're going to use its vertical intercepted arc. Oops. And that's going to be N to K. So the example we can list is that angle 1, the measure of that angle, is going to be half of LJ, the length of that arc, plus NK, that arc. And then we're going to take half the sum. So the last one is dealing with exterior angles. When you see exterior angles, we're going to take half of the difference. So that means we're going to subtract of the two intercepted arcs. There's two ways you can have that form, with two secant, or secant and a tangent. So they're trying to show you that, I'll have to erase this little part here, but I think they put angle 1 there. That angle 1 is going to be half of the difference, so we're subtracting. The arcs have to be inside of the angle, between the secant or the tangent. So like, if I look at the second example here, this is a secant because, oops, that's crooked. Let me fix it. Go back to where we were. This is a secant because it intersects, sorry, it's so crooked, the circle at 2 spots, here and here. And then if I highlight the other one, this is a tangent because it only intersects the circle at 1 point. But the arcs we're going to use have to be between our 2 segments, our secant and tangent. So the major arc here, which is x, and then we're going to subtract that minor arc there, which is y. So that angle that we have, the exterior angle, is going to equal to half the difference, so half of whatever the measure of arc x is, minus, that's the biggest arc, minus arc y. And so that is our notes, our video notes for angles related to circles, dealing with interior, exterior, and inscribed angles. So get this added. If you have it, I'm going to stamp it and give you some bonus points. Thank you.